Hi, my name is Jacqueline Hardy, and thank you for joining me after seeing my little teaser. So I attended the CSCI E89 course on deep learning in fall 2022 at the Harvard University Extension School, and this is my final project on recognition of emotions from images. So let's see. Facial expressions are an interesting feature that everyone has, where little micro expressions, little ways that we move our eyes and our mouths show other people how we feel. There are experts that say facial expressions are universal, and there are experts that say that they are not universal. In my opinion, facial expressions are universal, and this can be even displayed within these pictures below. So Paul Ekman, a psychologist, said that there are 6 main facial expressions, and that is anger, disgust, fear, happiness, sadness, and surprise. Later, he said there's a 7th, and that is neutral. So this data set that I am using has a total of 7 emotions, and let me turn on my pointer. So here you can see these are all images of anger, here disgust, fear, happiness, sadness, surprise, last but not least, the neutral. So let's look at the data. The data that I downloaded from the Kaggle website was a data set for building a neural network on recognition of facial expressions. There were 2 data sets included, a trained data set and a test data set. The trained data set was then from my project was split to have also a validation data set. I used a 65-35 split. So my trained data set, which consisted totally of 28,709 images, was then split into train 65%, so 18,660 images. And my validation data set was thus 10,049 images. The test data set consists of 2 subsets, a public and a private, and each with 3,589 images. So let's look at the distribution. As there are 7 different emotions that are displayed or that are in the data set, we have values from 0 to 6, angry, disgust, fear, happy, sad, surprise, and neutral. As you can see, angry, fear, sad, surprise, and neutral have roundabout the same number of images, whereas happy has a very high number, almost double the amount of, for example, surprise. And disgust has very little number of images, 436 images. This could lead to issues when training the model because they're not evenly distributed. So what did I do? When I downloaded the data set, it was a CSV file. I imported these CSV files using pandas, and then I needed to reshape the column with the pixels. So we knew beforehand that the images that are in the CSV file basically are 48 times 48 pixels. So the shape then has to be the number of images, 48, 48, and 1. And of course, we have to divide everything by 255 so that we can normalize the pixels to have it not from 0 to 255 as RGB values would be, but to have it from 0.00 to 1.0. Then we have basically our X variable, but we also need our Y variable, which is the labeling, so the emotions, so I need to return those as well. And then to split the data, 35 and 65 respectively. And to have it be reproducible, I entered the random state equals 1 as I use the train test split function in Python. So let's look at how I did it. If I go here, so as you can see, I input image height and image width. Then here to prepare the data, so the data set that I put in, take the column pixels and then separate it where there is a space, and then basically reshape it to have the number of images with the image width, image height, so 48, 48, and then 1 for each row. Then I concatenate it, and then I have the Y values just returned, and the whole function should then return the X values and Y values. And let's see if it actually worked. It did. I have a total train, 28,709. This is, of course, before my split. And then let's look how I split the data. I split the data here to X train, X valid, Y train, Y valid. Use the train test split function. And then you can see here my total train X and the total train Y. The test size is 0.35, which is my validation size actually, not my test. Then I said it needs to be stratified and the random state has to equal 1 so that it is reproducible, my models. And then here, divided the values by 255 to normalize it. And let's go see the shapes. Just going to run it so that you see that it worked. The shapes are exactly what I needed them to be for X valid and X train, as well as Y train and Y valid. So let's go back here. Let's go into presentation mode and my laser pointer so that you can exactly see what I am talking about. So this is the first model I built. I built 10 models and then searched for the best performing ones and then went and tweaked those until I found a model that suits or has the best accuracy out of all of them. So this is my first model. I had 2 convolutional 2D layers, 2 max pooling layers, a flattening layer, and then 2 dense layers. I used the activation function relu, and I used padding equals same, and then the input shape, of course, 48, 48, and 1. As you can see, the green highlighted ones are the number of filters, which you can see here is also the number of output filters. Padding basically just means that when it is set to same, that around the images, there are evenly distributed zeros on the top and bottom and left and right, so that when the filters go over, they do get every feature out of the image themselves. And here, what is circled in blue is the input shape. This can be also seen here, and that is the shape of the X variable, so the pixels. So then, after you build the model, you have to compile it. All of the models use the same optimizer loss and metrics function. So the optimizer function that I used was Atom. I used Atom because it's very efficient and time-friendly when training neural networks. For the loss function, I used the sparse categorical cross entropy, which is used when there's a multiple classification, which is in our case with the 7 different labels. And I used metrics accuracy. And then here you can of course see the epochs and the batch. Epochs is set to 10, and I chose the batch of 64 just randomly because we've been using it in class. And here you can see the validation data set that we created with the split. And as you can see, my first model didn't predict really well with 49.26%, and in the private test with a 50.91%. So let's look at the graphs of the training and the validation loss. As you can see here, we start to have a gap, and also here. So one could guess overfitting because the model is too simple for this data set after about 5 epochs. So this is the accuracy of my 10 models on the public and the private test set. So the two top models were 9 and 10, and 7 and 8 come very close to each other. I, however, chose then model 7 to be my third one, as here I have the highest value in accuracy. So this is the final model. As you can see, it doesn't look anything like the original model, the first model where we started off. Yes, we still have the convolutional 2D layers, layers followed by max pooling, and some even are followed by a dropout layer and even batch normalization. What did stay here on the bottom is the last one, which is the dense layer with the 7, and the activation here is softmax. So let's see, after I compiled the final model, after 100 epochs, the validation accuracy was 60.51, which is not to its full potential yet. So I then recompiled the model for 200 epochs and ended up on having a 62.69 accuracy on the test data set. So this is what the final model looks like when we look at the graphs, and we can see it was somewhat, I would not have needed to train it for 200, 150 would have been enough, because as you can see, the gap starts to get larger at around 115, 120, and here a bit later around 140. So, I mean, the lines are pretty close to each other, closer than they were before, but we still have a possibility of overtraining the model. So let's look at some predictions on the public and on the private set. So for example, here, angry. The neural network says it's a sad face. I would maybe understand why, just the way that the person is looking. But here, definitely, you see the anger in his face, and the CNN says also angry. Whereas here as well, even though fear comes really close, happy is higher. And here as well, the woman is sad, and the neural network notices this and labels correctly. Let's look at disgust. As you can see here as well, here the CNN believes it's happy. Here it's disgust, so this one classifies it correctly. The green one seems to be classifying disgust fairly well, whereas the yellow model, the public test, close to little. Now, we don't need to look at all of these. Basically, I'm just showing that this is what the prediction looks like. So here's a summary of all my models. As you can see, the 10 models we looked at before. And then 9, 10, and 7 were then what did change were the epochs, of course. And at one point, I switched from the batch of 64 to a batch of 128. And my best model showed on the private test a 63.56% accuracy. And this is the best model that I was able to create. So thank you very much for watching, and I hope everyone has a nice winter break.